Anybody remember what a buffer is?
Weak acid or base with its conjugate.
Thank you. Mina, what's a buffer? What was it? I didn't hear it.
Lies.
You don't really know, do you? All right. Weak acid?
It's a weak acid or weak base, and then it's like...
And it's conjugate. So you've got a solution that's got both components in it. You've got a whole bunch of acid particles and a whole bunch of base particles. That's what makes it a buffer. What a buffer is good for, I think of it as, and I mentioned this yesterday, think of it as like the guardians of a solution trying to keep that pH constant, like protecting the integrity of the whole solution. That's kind of what a buffer is doing. So if you throw, if you attack it with sodium hydroxide or hydrochloric acid, there are particles that can neutralize those attacking things and keep the pH fairly constant. Now the pH does change a little bit because that ratio of acid to base changes, but it keeps it pretty narrow range. Sir?
Would the water diluted making the pH different? Is that the reason why? Oh no, pH wouldn't change based on...
Yeah, there's not enough water created. There's a little bit, but it doesn't really change. It's that ratio of acid to base we're going to find out. Okay, so we learned yesterday about the HF and F minus buffer. That buffer has a pH of around 3 point something. We did the calculations for that yesterday. 3.14, I think it was, right? Pi. We're going to do another buffer today, a couple other buffers, but I'd like to start today with the ammonia and ammonium buffer. This is a case where we have a weak base and its conjugate acid. In this buffer system, what I'm asking you to do, there's nothing being added to it. It's just, okay, here's a solution that's got ammonia and ammonium dissolved in it. What is the pH? There's two ways that you can do this. Please don't start doing the problem. I'm going to ask you different groups to do different things. So just look for right now. One way you can do this thing is treat this as an ammonia solution with NH3 like your dominant substance, and it's acting as a base, taking a hydrogen from the water to make ammonium and hydroxide. Because it's acting like a base, we'd have the Kb of ammonia. Would you be able to find the pH knowing the initial concentrations of those things and filling out an ice table and finding the pOH, then the pH? Yeah. I think you could do that. Another way to do it, though, is to treat it as it's an acid solution, where the ammonium ion, NH4, is giving a hydrogen to the water to make ammonia and H3O+. In this case, because this is acting like an acid giving a hydrogen away, we need a Ka value. Could you find the pH this way? Where you know the initial concentration of the ammonium and the ammonia, and you know the K, so you should be able to find the pH. Now, some people earlier today were asking, what's that water? Why do you have the water there? Do you need it? The answer is no, you don't need it. You can just have NH4 yields NH3 plus H plus. That's fine. I just had it. I don't know.
But for the water, why would you need the water?
Yes, because it's got to take a hydrogen from the water. Yep. This part of the room, from Jennifer over, would you do the first, find the pH from this chemical equation using this Kb, and assuming ammonia like is the dominant thing. This side, you're a little smaller in number. You okay with that? Would you do the bottom part and use the Ka for ammonium and determine the pH for this? Now, please collaborate and talk about it, talk your way through doing this thing, because I know it was just new yesterday. But go ahead and try that, and then I'll ask you to report back. Yes.
So we did an example with adding OH and HF, a buffered solution of HF, comma F minus. But what if you were to add more H plus ions? It would combine with the
More than what?
Huh?
More than what?
More. I mean, as much as OH ions, we add H ions instead of OH ions. So then, wouldn't they combine with the F minus ion?
Yes.
Change the pH right? By a huge amount.
No, just by a small amount because it's a buffer.
I feel it was only for OH though. Because if we
No,
add,
it could be for strong acid too. If you have a buffer and you add either a strong base or a strong acid, the buffer will neutralize that added stuff, whichever it is, and keep the pH pretty constant. It changes a little bit, but not much.
because we have more F ions which makes it go to the left and stay at
Wait, so what H4
HF, right?
Uh-huh.
But by adding more H's, we would add more
It should be
H's,
You get more HF because more HFs are gobbling up
which
pH.
means that it would become more basic.
No. Because you're removing some of the base from your buffer.
No, we're
It's
adding
more acidic.
hydrogens.
Yes, which is gobbling up the F minuses, which is removing base from your buffer.
Oh, so it doesn't really it doesn't really change it that much.
Not that much. It does change, but not much. That's what a buffer's good for.
Got it.
Okay, get that pH.
Nothing.
What?
Got the pH?
Yeah.
All right.
No. Just a medium. All right, got it. Thanks.
So I'm just going to pause. I don't want to go too fast because I want you to try to process through this. I'll get you in a minute.
I can't.
Yeah? You got this, Kate. You got this. So you had 1 molarity of that, 1 molarity of that, right? 0 of that. I trust you. Got this?
Could we
Dang
work
it, I did
backwards?
it wrong.
Like if we want a pH of 4 and then work backwards.
You could. Yep. Trust me, the Zoom dolls will have you doing that.
Oh.
Oh, yes. They can do lots of things with you.
So for the H2O, we don't.
Just ignore it. Yeah. Okay. What do you have in pH?
Oh my god, 9.25.
9.25. Can I get a witness
I don't know.
from others?
9.26.
Same here.
Okay, I'll give you a range here, 9.25 to about 9.26. We're maybe somewhere in that range. Group over here, how'd you do with this way? 9.25?
Shoot.
Okay, so what do you conclude? You can now notice that we went about it 2 different ways. We were assuming that the NH3 was dominant, so we used the Kb. Over here we assumed that NH4 was dominant and used its Ka, wound up getting the same pH value. So what that shows us is that when you have to deal with a buffer solution, you can treat it as an acid solution like this, or a basic solution like this. Just make sure you use the right K, and your pH will be right either way. There's 2 ways to do these problems, to find the pH.
But the type of buffer it is dependent on whichever is stronger.
Yes, I was just going to say that. You're very insightful. Notice that this buffer is a basic buffer. It's got a pH in the 9s. The HF buffer that we did yesterday,
No, yeah, that was pH. You know why?
right here, this had a pH of 3.14. It was acidic.
If you're trying to, if you do negative,
John He, why was that?
if you do negative, you get pH.
Because HF is a stronger acid than F minus is as a base. So the Ka was stronger here than the Kb for that thing, so it's acidic. And then for NH3, the Kb of NH3 is higher than the Ka of NH4.
Hold on, I got my.
Sorry, Shweta. You got what?
My pH was wrong.
And do you know why?
No.
Did you use 1 molar and 1 molar? You had, what you were over these, right? Did you get 3 point something? Or 4 point something?
I got 4.7.
Oh, yeah, it's because you found the POH. Subtract 14.
If you multiply the two together,
Right.
we get 10 to the negative 14.
Those 2, yes.
Okay.
Very nice. Now the next thing that I'd like to do is talk about another buffer, and we're going to go through some of the calculations that we did yesterday. It's totally normal to feel like, gosh, I don't really feel like I'm getting this because it's just different. And don't think other people around you are getting it a whole lot faster than you are, even if they're like shouting out answers or whatever. They probably are just not really understanding totally. So whatever questions that you have about this, just stop me and ask. And don't feel badly about it. And don't feel like, oh, I don't want to do that because other people are going to think I'm stupid. Ask anyway. Yes.
So these two methods they're just two different methods of finding the same pH.
Yes. Right.
They're not two different steps.
Yeah, that's right. That's right. Just do one of those because either way you're going to get the same thing.
Were you going back to the slide that we were gonna try to visit yesterday?
I decided not to do that until later in the chapter. That how to make a buffer thing. I don't think that helps right now because we don't really understand it as well. So we'll come back to that. All right. Sorry.
We were kind of excited about it yesterday.
Oh, I'm still excited about it, but we're not ready yet. 2 molarity of HNO2 and then NaNO2. A lot of people earlier in the day were complaining about the Na. Don't be confused about the Na. It's a spectator. It breaks off of the NO2 as soon as it dissolves. It goes off and does nothing. Don't be distracted by it. It doesn't have to be part of any chemical equation. We're just treating this thing as an ion, not caring about what its counter ion is. Okay, we care about the NO2. It's got basic properties. The Na positive has no properties. It's just there. It's not acting as an acid. It's not acting as a base. It's not doing anything. So the first thing that we do is get the pH. This is just like the ammonia example we did on the previous slide. We know the concentration of each of these. We have an ice table. So if you need to find the pH of a buffer, just go right to the equilibrium. And another thing that people were telling me was confusing earlier today is yesterday, if I can just interrupt you for a second, I know there's a lot of people writing things down. I'm going to go back. The slide that had the floor cleaner on it, there it is, the floor buffer. I had given you 3 steps here, and I said, hey, put a box around these. You need to make sure that this is the steps that you follow. But look at what it is. This is for when you have a buffer and hydrogen ions or hydroxide ions are added. That's when you use these 3 steps. If I give you a problem and I just say, here's a buffer, find the pH of it, you don't have to do these. Just do step 3 and use the equilibrium constant to determine what the pH is. So let's take a look at how we do this. That's all I'm asking you to do here is give the pH. The solution's not being attacked by a strong acid or strong base, it's just sitting there. Yes?
Yesterday for one problem, you had like an arrow that's going just straight to the right.
Yeah, that's when you have a strong acid or strong base added to a buffer. And then you're going to have a complete reaction. For no disruption of the buffer, it's always equilibrium. All right. Now with this equilibrium, we know what the initial concentrations are. 2 molarity of that, 2 molarity of that. This reaction has to shift to the right because you can't have 0 of something in equilibrium. It's got to be some positive value. So I'm just going to uncover the rest of this. The Ka of HNO2 is given to us. Would you be able to do the ice table and come up with the pH? I think so. It's got to shift to the right. So minus x and then plus x is, and go ahead and determine the pH.
Should we always check for 5% rule, or should we just assume that?
You're putting me on the spot, Jennifer.
My job.
Just use it.
So we got that recording, right?
I got you, Jennifer.
This is what once you do the ice table, it's going to be x. There's no x squared term up here if you're using the 5% rule because this plus x goes away, that minus x goes away. So it's just 2x over 2 equals this number. Okay, so we can find the x value. That's the hydrogen concentration. What do you get for the pH?
3.4.
Give me one more sig fig. 3.4. Okay. 3.40.